Hello there. Come closer, don't be shy. My name is Pythagoras. You might have heard of me. I lived a very long time ago on an island in the Aegean Sea called Samos. It was a world of marble temples, sun-drenched olive groves, and a sky filled with the same stars you gaze upon tonight. I was a philosopher, a mathematician, a seeker of patterns. I believed the entire universe could be understood through the elegant language of numbers. It was a radical idea back then, but it's the very foundation of the world you live in today. I want to share a discovery with you. A secret that I and my followers whispered about in our school. We saw it as a key, a fundamental rule that governed the very fabric of space. First, let's find our main character, the right-angled triangle. You don't have to look far, they are everywhere, hidden in plain sight. See the corner where two walls meet the floor? That's it. It's a shape with three sides, but its defining feature is one corner forming a perfect square, an angle of 90 degrees. This special corner is the key. The two sides that meet to form this right angle are the legs, A and B. The third side, always the longest and opposite the right angle, is the hypotenuse, C. Remember their roles, two legs and the hypotenuse. My theorem describes a beautiful, unchanging relationship between these three sides. It's an elegant rule that connects them in perfect harmony. The rule is this: a squared plus b squared equals c squared. A simple statement, yet profoundly powerful. To truly understand squared, let's visualize it. Imagine building a square on each side of the triangle. My theorem proves that the area of the square on side A plus the area of the square on side B will perfectly equal the area of the large square on the hypotenuse, CE. It's a cosmic balancing act, a harmony written in the language of shapes. This isn't just an abstract idea, it's a fundamental tool of creation and discovery, used for centuries to build our world and navigate the stars. To truly understand the power of the Pythagorean theorem, let's walk through a couple of classic problems. We'll see how this simple formula A2 plus B2 equals sine C2 can be applied to find missing lengths in right-angled triangles, starting with a purely mathematical example and then moving to a practical scenario. Let's begin with a foundational example. Imagine a right-angled triangle where the two shorter sides, the legs, have lengths of 3 and 4 units. Our task is to determine the length of the hypotenuse, the side opposite the right angle, which we label C. We apply the theorem, A2 plus B2 equals sine C2. We substitute our known leg lengths into the formula, 32 plus 42 equals sine C2. Calculating the squares, we get 9 plus 16, which equals 25. This tells us that CE2, the square of the hypotenuse, is 25. To find the length of C itself, we take the square root of 25, which is a perfect integer, 5. So, the hypotenuse is 5 units long. This 3-4-5 combination is a famous Pythagorean triple, a beautiful example of numerical harmony. Now let's apply the theorem to a practical situation. A 13-meter ladder leans against a vertical wall. Its base is 5 meters away from the wall on the ground. The question is, how high up the wall will the ladder reach? This scenario creates a right-angled triangle, with the ladder as the hypotenuse, CE, the ground distance as one leg, B, and the wall height as the other leg, A. We know the hypotenuse, 13m, and one leg, 5m, so we rearrange the formula to solve for A. A2 equals sine C2, B2. Let's plug in our values. A2 equals 132 minus 52, which is 169 minus 25. That leaves us with 144. Finally, we take the square root of 144, which is 12. The ladder reaches 12 meters up the wall, a straightforward calculation with a very practical result. Imagine you're in a rectangular park at the southwest corner, wanting to reach the northeast corner. You could walk along the edges or cut diagonally. The edge route is 120 meters east, then 50 meters north. But how much shorter is the diagonal path? The paths form a perfect right triangle. We need to find the hypotenuse, the diagonal path, where A equals sine 120 and B equals sine 50. 1202 plus 502 equals sine C2. That's 14,400 plus 2,500 equals 16,900. The square root of 16,900 is 130 meters. The edge root totals 170 meters, but the diagonal is only 130 meters. You save 40 meters by cutting across. This is everyday optimization, finding the most efficient path using my theorem, whether crossing a park or plotting a spaceship's course. So far we've started with a known right triangle, a powerful piece of information, but what if we approach from the other direction with less certainty? What if you know all three sides of a triangle but don't know if there's a right angle? This is a question faced by builders and designers for centuries. This is where we use the converse of my theorem. It flips the logic around. It's not for finding a missing side, but a tool for checking, for verifying, for proving the existence of a right angle itself. The converse states, if you have a triangle where the square of the longest side, C, is exactly equal to the sum of the squares of the other two sides, A and B, then you can know with absolute certainty that it's a right-angled triangle. The angle opposite the longest side will be your 90-degree angle. Let's make this practical. Imagine setting up a tent. The instructions say the base must be a perfect rectangle for stability. You measure one corner, one side is 7 feet, the adjacent side is 9 feet, and the diagonal across is 11 feet. Is the corner square? Let's test with the converse. We check if 72 plus 92 equals 112. That's 49 plus 81, which is 130, but 112 is 121. Since 130 does not equal 121, the equation fails. The corner is not a right angle. Your tent base is skewed, not rectangular. This simple calculation has saved you from a wobbly shelter. You'll need to adjust the pegs until the numbers match. The geometry has revealed the truth. A woodworker builds a bookshelf bracket. For the shelf to be level, the bracket must be a right triangle. He cuts sides of 10, 12, and 15 inches. Testing the converse. 102 plus 122 equals sign 100 plus 144 equals 244, but 152 equals sign 225. Since 244, 225, the angle is not perfectly square. Thanks to this mathematical check, he can recut the piece before it causes problems. This is the theorem as quality control. A land surveyor verifies a triangular property with sides of 50, 120, and 130 meters. The deed claims a right-angled corner. She calculates 502 plus 1202 equals sign 2,500 plus 14,400 equals 16,900, and 1302 also equals 16,900. The equation balances perfectly. The surveyor confirms the deed is accurate. The corner is indeed a true 90-degree angle. The ancient knowledge guides modern precision. We've journeyed from ancient Greece to your modern world. This simple idea, A2 plus B2 equals sine C2, is more than a formula to memorize. It encourages you to see hidden triangles everywhere, in roof slants, bridge bracing, shadow paths. It trains logical thinking. This problem-solving skill extends far beyond triangles into every aspect of a well-examined life. The universe is knowable, you just have to look for patterns. Remember the harmony, the perfect balance between the squares on the sides. You hold a key, a secret passed down through millennia. A secret that reveals the simple, beautiful mathematical dance connecting every corner of our shared cosmos. The next time you see a right angle, think of this journey. The universe has rules, and now you know one of its most fundamental ones.